Alex Floor doing the Lab 5 home video lab report. We are going to be observing two objects, paper falling, which is the light object, and the clicker falling, which will be the heavy object. The main results that we hope to find are that using the FNet with just gravity and using the FNet with just gravity and drag, we hope to observe two options and find the correct drag coefficient. We hope that when objects reach a high enough velocity that their FNet, when using gravity and drag, will go to zero. We will be using Newton's second law of motion or the equivalent momentum principle. So we have the two videos here. This first one will be for the paper. We calibrate it using the calibration stick, and we set the axis so that this direction is the negative x-axis, and we looked as the object fell and plotted it in time. The time frames are approximately 1/30 seconds for both videos. And here's the data collected, and here's the graph. This is the second video. Again, we calibrated it and watched as it dropped. This is, again, the negative x-axis, so we calibrated in time. So then we made a program in Python that was similar. This box is the paper with just the effects of gravity, paper with the effects of gravity and drag, similarly for the clicker here. So we had the approximate weight of the paper was 0.0045 kilograms, and we plotted this as we did it in Python. So we ran the module, and we see that it's fairly linear when it's just gravity. We then go and look at the model of when gravity and drag are being used. We found that the appropriate drag coefficient is 0.045, which will later be explained when looking at the charts. So here's the model, and you can see that it is not nearly as linear and is curved. So we then go to the graphs of each one. This is similarly set up as it was in the last screen, which is paper with just gravity, paper with gravity and drag, similarly for the clicker. As you can see, when it is just gravity being looked at, the data is not very similar to it as it was in Python. It is quite off, almost 6 feet off. So when we did use the drag coefficient as seen here, the drag coefficient using that, the data becomes very similar. This is the same for the clicker. It is off when just using gravity, and when we use the drag coefficient, which is approximately 0.145, the data becomes very similar to the video recorded from Tracker. So we want to know what this means, and if we have an object and looking at the velocity, and these are the graphs of the object's velocity with the effects of gravity and with the effects of gravity and drag, we see that a terminal velocity is reached a lot quicker when using the effects of gravity and drag. This is because drag is a force opposite to gravity. We know that as an object's velocity increases, the effects of drag also increase, and we know that gravity and drag become equal and opposite, and once this happens at fast enough velocities, there's no net force causing the velocity to become constant, and this is effectively the terminal velocity. So now we want to know, what if we throw the object instead of just dropping it, which means the initial velocity is no longer 0. And for this we chose a number of -3 meters per second, which means it was being thrown down. And as you can see with these two graphs, the terminal velocity is reached at a much quicker rate for the object being thrown as opposed to the object just being dropped. And we're going to be looking at the object with velocity, or the velocity of the paper with gravity and drag, because we know that is more accurate to what actually happens in real life. The terminal velocity is reached only when speeds are high enough, or when the velocity is high enough, and the terminal velocity is reached quicker when the object is thrown, and this is because the object being thrown has a speed that is closer to the terminal velocity. So this was my lab video. Thank you very much. And as a fun fact, a human's terminal velocity is about 120 miles per hour.